So for this learning module, we'll introduce the concept of a couple and talk about how to compute the moment of that couple. So you're most likely familiar with couples from your experience in driving a car. And if you've ever driven an older car without power steering, one of the things that you may have noticed is particularly for larger vehicles, the wheels are often larger. And when you think about the nature of the forces that you apply when you turn the wheel, naturally, usually, if you're doing it correctly, on one side you're kind of pushing up, and on the other you're pushing down. So you have forces which ideally are equal in magnitude, but they're opposite in direction. And what that force pair does is only induce rotation in the underlying wheel. So that's what a couple is, and we'll see that formally in the next slide. But the thing that I wanted you to realize most is if you're trying to turn a wheel type shape or really induce that kind of motion in any body, the wider that you spread your hands, the easier that it is, the less the force has to be to induce the same amount of rotation. So that's a principle that's pretty similar to what we talked about a lot so far when talking about pushing doors open or turning, using tools like wrenches and pliers and these sorts of things. So a couple is technically defined as a pair of forces which have equal magnitude, opposite direction, and they're separated by some distance. You can compute the moment of a couple by two approaches, just like standard moments about a point or moments about an axis. All you have to do is take the magnitude of either of the two forces, they're the same, and multiply by the perpendicular distance separating the two. And you can kind of just determine the direction, as we'll do in one of the examples here, by just using your own physical intuition, particularly for coplanar force problems. In addition, we can have a vector approach. That's always valuable because it doesn't require us to kind of use hacks and rely on having certain geometrical information presented to us. And if we do that, the key point is your position vector just goes from any point along the line of action of one of the two forces to any point along the line of action of the other two forces. So naturally, it's most convenient, if you can, to take it in the perpendicular direction directly across. So what do you need to know about couples? Well, since they have equal magnitude and opposite direction forces, if they're acting on a body and I compute the resultant effect of the two forces in the couple, it's zero. And what that means is that they won't tend to translate the body at all. The effect on the body will be purely rotational. And because of that, the moment of a couple is a special kind of vector known as a free vector. And what that means is that its effect will be independent of where it's applied on a body. So if you think about that, if you say you're like turning a steering wheel and you have a particular force at a particular diameter separating, that will induce a couple. The effect of the rotation on the steering wheel is the same if you were to put your hands in a little bit and just turn a little bit harder, right? In terms of the net effect of the motion of the body, it's still a rotation in that amount, regardless of the point of application of the forces. So since couples are moments and moments are vectors, of course, we can add them using all the traditional vector rules of addition. So let's look at a couple of example problems. We have a beam and we have two force couple pairs acting upon the beam. And we want to know what do those forces F need to be in order to induce a resultant couple of 1.5 kilonewton meters in the clockwise direction. So I'm going to go over to my .cam. No, I have a printout of this. So I want basically the resulting couple to be, let me look back at that, 1.5 kilonewton meters in the clockwise direction. Okay, so let's talk about the solution here. Well, the resultant couple, so you can call it resultant, is just going to be the sum of the two couples that are acting upon the body. So we need to compute the moment associated with this force couple pair, along with the moment associated with the unknown force, what we don't know. And what we'll see is that we still will have one equation and one unknown that will let us solve for what this force is. So let's do it. Step one, let's compute the couple of the 2 kilonewton forces. So first of all, just make sure it is a couple. Notice that they have equal magnitude, opposite direction, and their lines of action are perpendicularly separated by 0.3 meters. And what that means is that I can just write m of 2 km if I would like. Going back to our scalar formulation, since this is a simplistic setup, I can say it's the magnitude of the force, 2 kilonewtons, times the perpendicular distance separating, 0.3 meters. And I notice just physically, if I kind of put one finger on each of those two forces and imagine rotating the body in the direction that they would induce rotation, that's in the counterclockwise direction. So we usually refer to that with a positive sign convention. So this is going to be 0.6 kilonewton meters positive. Step 2, basically express the couple associated with the unknown force F. So if I do that, the couple associated with F, and again, I think part of what confuses people about this is half the time I'm calling it a couple and half the time I'm calling it a moment. Remember that a couple is just a special type of moment that's induced by these two forces that have the three required properties: equal magnitude, parallel lines of action, opposite direction, and separated by a perpendicular distance. That's another way to say that is that line of action comment that I made originally. So what would this be? Well, it's just going to be the magnitude of the force, which I don't know, multiplied by the perpendicular distance. And I will just kind of not worry about units and know that since this is in meters and this is in meters, the units of force will be whatever the units of the known force we have, or kilonewtons. Now, the one thing to be careful about this, if you kind of put your fingers on the paper and look at the rotation that it would induce, it's actually going to be in the clockwise direction. So that's going to be called a negative. So this is going to be minus 0.9 F. So what we know is that if we add these two things, 0.6 minus 0.9 F, we want them to be equal to, well, we wanted this result to be 1.5 kilonewton meters in the clockwise direction. Remember that the clockwise direction is actually negative. I should have said that beforehand. Counterclockwise is positive. So we want this to equal to negative 1.5, and kilonewton meters, we're still all consistent. So what that means is that I want my F to be, you just solve this algebraically, 1.5 plus 0.6, and that will mean that F is going to be 2.1 divided by 0.9. And I already put this in a MATLAB because I got to this point in the recording and I got a call. I had to stop, unfortunately. So it's 2.33 is the number to 3 sig figs, and it will just take on the consistent force units that were used around the problem, which is kilonewtons. So that's how I do that problem. So let's go to the second problem in the PowerPoint. So what we're asked in this case is to compute the couple moment of the force pair shown to the right in rectangular form. So this is kind of a three-dimensional type problem, and it's really hard to see, but we will do our best. It's a low-resolution image in the book PowerPoints that they provide. So clearly for this example, we'll prefer a vector approach. So what we need to do is write an expression for a position vector between the two lines of action, along with an expression for one of the two forces in Cartesian form. So I'm going to choose, and the key is like just picking which of the two forces you want to use. I'm going to choose to use the force at B just because that position vector is very simple. It's just 0.4 meter displacement in the x direction. So I'm going to use this as my position vector. So I will say RAB is just 0.4 meters. And then how would I write FB in terms of its rectangular form representation? Well, notice it's going to have this is its magnitude, 450. This is going to be in the z direction, so that's minus z. And this is in the plus y direction, so it's in the zy plane at a fixed x value. And it's going to decompose using a 3-4-5 geometry. So what that means is since I want this angle here, theta, I can say sine of theta is opposite divided by hypotenuse, which is 4/5, and cos theta is 3/5. So I actually don't need to know what that angle is in order to say that the z component of FB, which is right here, it's going to be adjacent to that, will be minus 450 times cos theta, minus, because it's going in the negative direction, and that will be minus 450 times 3/5. And we'll compute what that is in a minute. For the y component, that's in the positive y direction. It's just going to be 450 times sine of theta, which will just be 450 times 4/5. Therefore, I can write an expression for FB. It has no x component. Its y component, let's go over here and do this, is going to be, so I'm just going to define this vector in MATLAB. 0, 450 times 4/5 for the y component, And 450 times negative 3/5, or just make sure you have a negative in there somehow. So that's your FB, 0, 360, and minus 270. And that will be in whatever units of magnitude we were given, which was newtons. And our position vector was in meters. So therefore, we can say, going back to the dot cam, that the moment of this couple, which is still just a moment, is just going to be R cross F, which is going to be, you're going to compute a cross product, where in the second row, you have the position vector, which is 0.400. And in the third row, we'll have the decomposed force vector, which has 0x component, 360y component, and minus 270 z component. And I've shown you how to do those cross products a few times. So just to save you time, I'm going to just go ahead and use MATLAB for this. And this is an easy one to compute where there's only, back to the dot cam just to show you why I'm saying this, because there's so many zeros along this row. Remember, when you do your cofactor expansion, you're basically, let me just show you just in case anyone is only watching this video. In terms of getting the I hat component, it would be I hat times the determinant of this matrix. So notice that that's going to be just 0, which means that that force will not tend to induce a rotation. That couple, rather, will not tend to induce a rotation about the x hat direction. And I can kind of go back up to the drawing and show you why that is in a minute. Minus j hat, determinant of 0.400 minus 270, and then plus k hat, determinant of 0.400 and 360. So you are going to have a j and a k component, but a little bit easy because you don't have that I component. But I can show that by just taking cross of R and FB, and I get 0x component, as I knew, 108y component, and 144j component. And that will be in units of whatever the units of the force were times the units of the position vector. So Newton meters. And it's not surprising that this doesn't have an x component, because if you kind of look, so just so everyone can see what the answer is, if you look at how this plane lies, that it's going to, so the moment is going to be about an axis which is perpendicular to the plane that's formed by these two vectors. So if you think about that, all the rotation will be about an axis like that. There will be no rotation about the x-axis, which is why that is turning out to be 0. So hopefully the idea of computing the moment of a couple made sense. Just know a couple is a particular scenario where you have two forces which are equal magnitude, opposite direction. They induce rotation only, and there's the scalar and vector approach to compute the moment associated with them, just like all moments that we've computed until now.